All right, welcome back to day 3 of our Introduction to Physics. Today's topic is vectors. So without further ado, I will go ahead and share my screen and we will get rolling in this. Oh, that was not the right one. All right, can we all see the slide that says vectors?
Yes.
Great, thank
Yes.
you. Woohoo! So yeah, I don't know how many of you guys have watched Despicable Me, but I'm a big fan of this movie because this scene is just so on point. But anyway, yeah, I think that this is a really funny way to get across the meaning of what a vector is. But also, vectors are going to be really important for us over the next couple of weeks because lots of different topics in physics will be based on vectors, or we'll be using vector math for a lot of the topics that we'll be talking about. So this is an important topic, and I'll be posting on Canvas later today. I'll be posting some resources for you to practice this if vector math is maybe not your strong point. So basically in the world, there are two different types of quantities. There are scalars and there are vectors. So scalars are kind of the more simple ones to think about. It's a quantity that just has a size. There's no direction associated with it. So these would be things like time or mass, dollars, distance, things like temperature. They just have a number associated with them. So this math that we can do with scalars is very, very simple and familiar to us. If we have two different times, we can add them together and get a time as a result. Or if we have two different masses, so 6 kilograms plus 3 kilograms, it's very easy to add those together and we just get 9 kilograms. Nice and simple. Scalars are good. Vectors, on the other hand, are a little bit more complicated because, like we saw in the Despicable Me clip at the beginning of this PowerPoint, they have a magnitude and a direction associated with them. And both portions of that are equally important to a vector. So if we just have a magnitude, again, that's not a vector. That's not enough information to be considered a vector. So examples of vectors would be displacement, which tells you not only how far away something is, but in what direction. So Miami is 300 kilometers away is distance, scalar. Miami is 300 kilometers south, that's our displacement, and that's a vector. Velocity is a vector. It tells us how fast we're going in a certain direction. Acceleration tells us how the velocity changes. Since velocity tells us a direction, acceleration will also tell us a direction. And then force, it matters not just that I push somebody, but that I push somebody down the stairs. That's a very different result than pushing somebody up the stairs, very, very different result. So the way that we represent vectors is with an arrow because that shows us both a definite length, so a magnitude, and it has that nice convenient arrowhead that shows us the direction. So arrows are the typical way that we represent vectors. And whenever we're measuring our angles, we'll always measure them counterclockwise from the positive x-axis. So if you're thinking about it in terms of like directions, in terms of like north, south, east, west, we always measure counterclockwise up from east towards north. And this is pretty standard way to measure angles in your math classes as well, most likely. So that's going to be kind of the general rule of thumb in terms of establishing our directions, our angles. When you see a vector printed in a textbook or something, it's almost always a bold letter with an arrow over top to show that it is a vector. The direction matters. If we're just talking about the magnitude of a vector or a scalar quantity, usually it's not bolded, or we'll see that same symbol for a vector with those absolute value bars around it, because the absolute value takes away the importance of the direction. Absolute value just means what's the size, and that's a magnitude. So distance versus displacement is one of the first kind of scalar versus vector issues that we come across in physics. So if I travel 5 meters left and then 4 meters right, I will have traveled a distance of 9 meters. Right? When we're dealing with scalars and we have these numbers that have the same units, we can just add them together or subtract them or whatever it is that we're doing to them. So in this case, to find the total distance that we traveled, we just add 5 meters plus 4 meters. So we've walked a total distance of 9 meters. However, your displacement is only 1 meter to the left, right? Because if we take a look at those two portions of our journey, the 5 meters left is a bigger magnitude than the 4 meters to the right. So instead of just adding them together, we have to take into account the direction that is associated with them. So 5 meters left plus 4 meters right, that 4 meters that we traveled back to the right kind of negates some of that 5 meters that we traveled to the left. And so our displacement is really like asking, where are you? Where did you end up compared to where you started? And so we ended up 1 meter to the left compared to where we started. So that's your displacement. If you, for example, go to the store and come back to where you were, then your displacement is 0, no matter how far away the store is. You could have traveled a huge distance, but your displacement will still be 0. So when we're dealing with vectors, the math is not always as straightforward, lol, puns, as it is with scalars. Right, with scalars, we can just add or subtract, very simple. Vectors, not so easy, because vectors can also be on angles. And so usually we'll need to know a little bit of trigonometry to deal with vectors. It can also help sometimes to just draw them graphically and see what's happening. So some basic rules when we're drawing out vectors. Remember, we draw them as arrows. The length of the arrow and the direction of the arrowhead are both significant when we're dealing with vectors. So let's say we've drawn our vector. We can slide it around, but we cannot change the length or the direction that the arrow is pointing. So if we have multiple vectors that we're trying to add together to figure out our displacement, then we can draw these vectors what's called tip to tail. So the arrowhead is the tip and the stick part of the arrow is the tail. So we'll draw one vector and then we can draw another vector putting the tail of the next vector touching the tip of the first. The resultant vector, which is the result of adding together multiple vectors, the resultant vector will begin at the tail of the first vector and end wherever the tip of the last vector is. So in the case where you're dealing with just two different vectors, it'll create a nice triangle. If we have more than two vectors, we can get all kinds of crazy different shapes. So I have here a link to a simulation, and I'm going to go ahead and show this simulation to you very quickly. This will be a great resource for you if you need some help kind of visualizing some vector problems. So I'm going to pause my PowerPoint and go ahead and pull up this site.
Are you able to copy that link to the chat, or are you able to send that to us?
Oh, that's great. I will try to do that. I'm going to be posting this PowerPoint on what's it called? YouTube. No, the video will go on YouTube. I'll be posting this PowerPoint on Canvas so that you have access to the notes later on. So I'll be posting that after class today. But let me put this link in the chat for you. Hold on one moment. All right, there it is.
Thank you.
Thank you for asking. Okay, can we all see the vector addition screen?
Yes.
Yes.
Thanks. Okay, so first we'll just start off with some one-dimensional vectors. So this would be like our example of going 5 meters left and then 4 meters right. So to play around with this, you can just click and drag a vector into this grid. I'm going to just have it start at 0 just for simplicity's sake. But we can drag this out to be whatever length we want. I'm feeling 15. Why not? And so up here, remember, this is the symbol for magnitude. So that tells us that the length of this vector is 15. It's not at any angle up from east or from our positive x-axis. So this angle theta is 0. All of its direction is along that x-axis. So, excuse me, so this vector A in the x direction, all of its magnitude is along that x direction. So this magnitude of 15 matches the magnitude of the vector. And since no portion of this arrow is going up vertical, that means our y component of the vector is at 0. Okay, so all of it is going towards the right. If I put in another vector, this would be adding them tip to tail. So you see how the tip of this first arrow is touching the tail of the second arrow? This would be adding tip to tail. If I put the sum in here, you can't really see it because it's kind of hiding behind there. So I'll drag it up here. The sum, or the resultant vector, goes from the the tail of the first vector to the tip of the last vector. It's that length. So in this case, vector A was 15 units. Vector B was 5 units, and so our magnitude of the resultant is 20, 15 plus 5. Nice and simple. However, if this vector B is going in the opposite direction, you can see what that did to our resultant vector. It shortens our resultant vector. So now, vector A is still going 15 units to the right. Vector B is now going 5 units to the left. So that's why the x component of this vector B is negative 5, because we usually associate positive with right and negative with left. And so this resultant vector is 15 minus 5, or 10 units in length. Okay. So one-dimensional vector addition is pretty simple. Let me stop my share real quick. I'm just going to stay on the same website and go back, but I couldn't do that because my bar was in the way. Give me one moment. Okay, so now I'm back here on the same launch page, but now we're going to do some 2D vector addition. And so in this section of the website, I guess, you can change the angle that you have the vectors at. So we'll just pick a random length and a random angle. So vector A is 17.5 units long at an angle of 13.2 degrees. And so now we're seeing that this x component and the y component are different. They're both different than the actual magnitude or the actual length of this arrow. So if you can imagine that we have like a big spotlight shining downward on this vector, the x component would be however much sideways this vector is going. So it'd be like the shadow that's cast down on the ground from this vector. That would tell us how far it's going in the x direction. So even though the total length of this vector is 17.5, The x component of it is 17. That would be how long the shadow would be if the spotlight is directly overhead. If instead we have a spotlight over here that's shining maybe like towards a wall or something, our y component would tell us how much vertical this vector is going. So that would be 4 units vertically would be the height of this vertical shadow. If I take a second vector, and again, I'm going to add it the same way, tip to tail. So now this vector is 10 units long. It's at an angle of 36.9 degrees. Again, if we imagine the spotlights kind of shining down and shining across, the amount of blocks sideways that vector B stretches is 8 blocks. So that's the x component, 8 blocks. Right, if we have our spotlight over here again and shine the light this way to see the shadow on a wall, it would be 6 blocks high because that's how many blocks up this vector goes. From where it started to where it ends, it's 6 blocks high. Now, if we look at the sum arrow or the resultant vector starts at the tail of the first vector and ends at the tip of the second vector. And so now we can see that this magnitude seems like it kind of comes from nowhere. Because remember, this A vector is 17.5 units long. The B vector is 10 units long. But this is not 27.5 units long as a resultant vector. So there's some kind of weirder math that we have to do when we're dealing with vectors on an angle, and that involves trig. You can also see that it's at a completely different angle than either of these other two. So we're going to pop back over to the PowerPoint, and I'm going to show you some of this vector math. But first, before I do, I want to just show you what would happen if we add in a third vector. Let's put it here. So our sum, again, would point from the tail of the first vector to the tip of the last vector. And you can see now it's not really completing a triangle, it's just completing the shape. So no matter how many vectors we're adding together, we can always draw them tip to tail, and the resultant vector, or the sum vector, will always start at the very beginning of the vectors and end at the very end of the vectors. Okay, let me stop my share, bounce back over to this PowerPoint, and we will continue. Okie dokie. So like I was saying, we have these vector components. So when a vector is off at an angle, even if it's not at a significant angle, if it's just an angle of 0, vectors can always be broken down into their components. So we saw in the simulation that that was denoted with a subscript x or a subscript y. So again, the x component is always going to tell us about what that vector is doing horizontally. And the y component is going to tell us about what that vector is doing vertically. So when we have a vector and we break it down into its components, this is how we see it written. This vector A is the sum of its x component and its y component. And those components are still vectors because they still have a definite length and they still point in a certain direction. So if we remember back to the simulation, right, our horizontal component along that x-axis was pointing in the positive x direction. So that's still a direction and it still had a definite length. So these components are still vectors. Both magnitude and direction is important for them. So if you have taken trig, you may have seen this kind of mnemonic device before called SOHCAHTOA. It's just a way to help us remember what the trig identities tell us about the angles in a triangle and how it's related to the legs of a triangle. So let's say we're adding together this red vector and this blue vector. And this green vector would then be our resultant, the result of adding together those two vectors. So this resultant, we can see, is off at an angle, theta. So in order to figure out what that angle might be, let's say we know all of the lengths of our vectors, all of the magnitudes. So the sine of our angle is the length of this opposite side divided by the length of the hypotenuse. And that's why the first part of this mnemonic device is called SO. Sine equals opposite over hypotenuse. Let's say we don't know what the opposite length is, but we know what the red vector length is. Then we could use the cosine of the angle. The cosine of the angle is the length of the adjacent side over the length of the hypotenuse. So that's this middle portion of SOHCAHTOA, ka. Cosine is adjacent over hypotenuse. If we don't know the length of the resultant vector at all, but we do know the lengths of the two vectors that made it, then we use the tangent. So the tangent of our angle is the length of the opposite side of the triangle divided by the adjacent side. Okay, so that's this last part, TOA. Tangent is opposite over adjacent. So depending what information we're given in the problem, that will lead to whichever trig function is most convenient for finding either the length of the hypotenuse, that resultant vector, or the angle that it's off at. Sometimes we'll need to find both, so we might need to use multiple trig functions, but I would definitely have these either memorized or written down somewhere very convenient for you to reference, like in the front of your notebook or something like that, because these are the main three trig identities, trig functions that we'll be using in physics. So we can do the same process for any kind of vector, whether it's displacement, force, acceleration, whatever kind of vector we're dealing with. We can use these same trig functions. When we're expressing these components, like I said, sometimes we can write it as, I just pointed at my screen like you can see what I'm doing. Anyway, sometimes we have it written down like this. This is the same form that I had on the previous slide, where we have the x component plus the y component. But there are all of these other ways that we can see it written as well. This kind of reminds me of like graph coordinates, right? You have the x coordinate and the y coordinate, except now we have the x component and the y component. So that's really helpful when we're adding and subtracting vectors together, just to have those magnitudes kind of laid out for you. This is called matrix form. The top is the x component and the bottom is the y component. Sometimes x and y are not called x and y. Sometimes they're called I and j. And if we're dealing with 3 dimensions, we'd have I, j, and k instead of x, y, and z. I'm not really sure how that one originated, but it can be confusing sometimes. So just remember that I corresponds with the x direction, j corresponds with the y direction, and if we have it, k corresponds with the the z direction. We may also see it like very explicitly written as this. The x component of our variable, in this case velocity, is this, and the y component is this. So usually I'll write them in this kind of form just because I think that makes it the most obvious. Or sometimes you'll see just the magnitude and the direction of the resultant written. You won't even see the components. So 19 meters per second at 105 degrees counterclockwise from east. So that really helps you with the angles because it expressly gives you the angle. These are all different ways of saying the same thing, and they have advantages and disadvantages. So you may see any of these in your textbooks or in your homework problems. Okay, so we can add x components together and we can add y components together, but we do not want to add x with y. That's kind of a no-no. So when we add two or more vectors together, first we break them down into their components, and then we add their components. So here we have two different vectors where we've broken it down into x and y plus x and y. And so that, again, makes it very clear. We just add the x's together. So 3 plus 2 gives us 5. And then we can add the y components separately. 9 plus -5 gives us 4. And so the resultant vector would have an x component length of 5 and a y component length of 4. To find the magnitude of our resultant vector, we would use this equation, the Pythagorean theorem, because we're just really adding two vectors here to complete a triangle. And so we want to find the length of the hypotenuse using the Pythagorean theorem. So the square root of our x component squared plus our y component squared. So in this example, 5 squared plus 4 squared, take the square root of that, and that gives us a resultant magnitude of 6.4 degrees. If you remember back to the slide where I was telling you about SOHCAHTOA and the trig identities, remember the tangent of the angle is the opposite over adjacent. And so here we don't know the angle, but we know the length of the opposite side and the length of the adjacent side. So what we're going to do is use an inverse trig function, an inverse tangent. And that's just going to give us the angle instead of, the tangent of the angle. So to find the angle by itself, or the direction, we take the inverse tangent of our y component divided by our x component, because that's the opposite side over the adjacent side, y over x. So the inverse tangent of 4 over 5 is 38.7 degrees. So this vector is 6.4 units long at an angle of 38.7 degrees. So you can do this process for any number of vectors that you have. You just add them in to the corresponding pieces. So adding in all of the x components to get your x resultant, adding all of the y components to get your y resultant. To get your magnitude, you just square all of the different components and then take the square root. It works for any number of vectors. Okay, if we're multiplying vectors by a scalar, it's very, very simple. All we need to do is multiply each component by that scalar. So here's vector A. It has x, y, z components, so 3, 4, 5 are the components. If we want to multiply the vector A by 2, then all we need to do is multiply each component by 2. So we get 6, 8, 10. If we're multiplying vectors by vectors, now it's a whole different beast called dot products and cross products. We will not get into that today. We'll hopefully get into that later once it's a little bit more relevant in context. Okay, before I go through this example, do you guys have any questions so far?
I have a question.
Yes.
When you add like the vectors together, so like with like the x, like the x and y's,
Yeah.
and if you have one that has 2 and then one that has 3, do you just add like the x and y's together in both of
So like
them?
up here?
Yeah.
Yep, so we just add the x's together and then we like set them aside. And then we add the y's together and set them aside. And so that's how we ended up with this resultant, the components of it, because we did 3 plus 2 equals 5. That's the x components. Separately, we do 9 plus -5, which is 4. And so again, we don't ever really combine x and y together. So we're not doing like 3 plus 9. That it just doesn't mathematically make sense to add together horizontal and vertical. You add together two things that are the same. Just like it doesn't make sense to add together apples and oranges to find out how many apples you have. Like oranges are different. So the x component and the y component are two separate things, apples and oranges. We have to only add together apples, x components, and only add together oranges, y components, and we have to keep those separate. Does that make
So
sense?
yeah. So then like if you so if one vector has like has like three like numbers, so like 1, 2, 3, and then like the other second one has like 1, 2, do you just would you add those two together?
You would just assume that the third component is 0. So
Okay.
like if one has 1, 2, 3, and the other vector is just 1, 2, we just assume that that third component of that other vector is 0, and so we didn't bother to write it.
Okay, thank you.
Does that answer your question?
Yes, it does. Thank you.
Okay, great. Okay, let me see how I'm doing on time. All right, okay. So here's an example. I put in example 1.5 in the textbook. If you have the textbook, again, if not, no big deal. But here is our first example. A cross-country skier skis 1 kilometer north and then 2 kilometers east on a horizontal snowfield. How far and in what direction is she from the starting point? So sometimes it can help when we're dealing with these sorts of problems to draw a picture or to try to visualize what's happening in your head. So I always recommend when we're dealing with vectors that you draw some kind of vector diagram or just like a sketch of the vectors, approximately how long they are, and in approximately what direction they would be going. So here's my sketch. I'm such a good artist. Okay, so she goes 1 kilometer north and then 2 kilometers east. The fact that she's on a horizontal snowfield means that we're not having to deal with a change in elevation. So we're just dealing with two directions and not adding in this third dimension at all. So we want to know how far she is from where she started and in what direction. So that's basically asking what is the resultant magnitude and direction. So based on our picture, we can see that she's making a nice convenient triangle. And so we can use our trig functions that we were talking about. So in this case, our first vector is purely in the y direction. There's no x component to it because it's just going straight up in our picture. And similarly, our second vector is just going purely horizontal in our picture. There's no vertical component to it at all. So we don't really need to break it down into its components because it kind of already is for us, right? This has an x component of 0 and a y component of 1. And this one has an x component of 2 and a y component of 0. So we can just use the Pythagorean theorem to calculate the length of the hypotenuse of this triangle or the resultant. So 1 kilometer squared plus 2 kilometers squared. Take the square root of that, and that gives us a magnitude of 2.24 kilometers. Now to find the direction that she's going, that's where we need to involve the trig functions. So if we look at our picture, we're trying to find this angle here. We know the length of the side that's adjacent to the angle. Adjacent means next to the angle. And we know the length of the side that's opposite our angle. So that means we're going to use the tangent. Because remember, in SOHCAHTOA, tangent is opposite over adjacent, and we know those things. Okay. We also now know the magnitude of the hypotenuse. So you could technically use any of the trig functions if you wanted to. But let's say you found the direction first before you found the magnitude, you would want to use the tangent in that case. Okay, so here's our identity for the tangent of the angle, opposite over adjacent. So in order to find just the angle, we take the inverse tangent of the opposite over adjacent. So the inverse tangent of 2 divided by 1 gives us 63.4 degrees. Okay. So there is our answer. Ooh. Do you guys have any questions about that?
Yeah. When we're doing assignments, would you like us to get exact values like square root of 5, or would you just like us to round it to the 100th?
Rounding is totally acceptable. I mean, either way would be acceptable for your professors. But you may find that if you have to do homework online or something like that, like mastering physics, if you guys have used that in AP physics, it will tell you what format it will accept. So it'll tell you how many decimal places that you should put in. For me, my general rule of thumb is 3 sig figs. That's kind of like a nice amount of precision. Um, but your individual professors may prefer something different when you get there.
All right, thank you.
Yeah. Any other questions? All right, let's try another example. So, after being left at home alone, Kevin McAllister realizes he needs a new toothbrush. To get to the store, he walks 9 blocks west and 3 blocks north. Each block is 1/8 of a mile. After which he must take a 0.35-mile shortcut northeast through a park to avoid capture by the police. How far is he from home now, and in which direction should he walk to get back to his house as quickly as possible? So again, my recommendation is always to start by drawing a picture and figuring out exactly what's happening in this scenario. So here's his home. He starts out by walking 9 blocks west, and then he walks 3 blocks north, and then he walks runs maybe, a 0.35-mile shortcut northeast. So northeast, that direction, implies a 45-degree angle in general. So we want to know the resultant, how far he is from home and in which direction he should walk. Okay, now there is a problem in this problem, and that's that our units are not completely consistent. So you should have remembered from yesterday that the units make a difference in your problem. Units are important. We can't add together apples and oranges. We have to add together blocks and blocks and blocks, or miles and miles and miles. So we need all of our units to be the same. Now we're given this conversion factor in the problem that each block, 1 block equals 1/8 of a mile. So this is 9/8 of a mile, or 1.125 miles. 3 blocks is 3/8 of a mile, or 0.375 miles. If you had wanted to, you could have put this 0.35 miles into blocks instead. Either way would have been fine as long as your units are consistent. And again, that northeast implies exactly halfway between north and east. So that's a 45-degree angle. All right, so there's our sketch. Now let's start solving the problem. We know that the magnitude of our resultant vector is going to be based on the Pythagorean theorem. And this angle is going to be based on one of our trig functions, an inverse trig function. So if we take a look at just our resultant vector here, we can see that part of it is vertical. So it's going to have a vertical component, a y component, and it's going to have an x component. Part of it is horizontal as well. So we need to find those components in order to use these equations. Okay. So now if we take a look at the vectors that we were given, this first one, this 9 blocks west, only has a horizontal component. And this last vector that we were given is off at an angle, so it also has some horizontal component. So remember, when we're dealing with x directions and x components, we can add the x's together. We can add the y's together separately, but we must keep them separate. Okay, so this 3 blocks is purely vertical component, just a y component. We also have a y component from our last vector there too. So if you take a look at this picture, our red vectors are kind of competing against each other a little bit, right? We have one going west and then one going back to the east. Our y components are purely adding together because this one's going north and this one's going north. So we're going to be able to just add those together. But we need to know how big the components are before we can actually add or subtract. Okay, so if we take a look at this portion, right, this 0.35 miles, this is the one that we really have to deal with because that's the one that's off at an angle. So we know the length of the hypotenuse of this portion, right, 0.35 miles. We know the angle. So now we're going to use the sine to find the opposite side, our y component, and we're going to use the cosine to find the length of our adjacent side, or the x component. So here's the trig function that I gave you, right? Cosine of our angle is adjacent over hypotenuse. If we do a little bit of manipulation to move that around and get just the adjacent side by itself, that means the adjacent side is the hypotenuse times the cosine of the angle. We can do a similar manipulation for the sine of the angle. And I'm just going to assume that up and right are positive and that down and left are negative. That's the general rule of thumb that we use. So our x component of this vector that's off at an angle, we know we have this negative 1.125 miles from this first portion of his walk. Now this is where we find the component that we get from this top portion. So the hypotenuse, 0.35, times the cosine of our angle, 45 degrees, is what we're going to add on to this negative number. So again, remember, these are vectors that we're dealing with. The direction is important. And the way that we signify direction in a mathematical equation is positive and negative. So since this first portion is to the left or west, that's negative. We're adding on a portion to the east, so that will be positive. But we end up with this portion negative 0.8775 miles. I see your guess there. We'll see if you're right. Oh, did it just kick me out of the PowerPoint? Are we good? We're good. Okay, anyway. Okay. So we're going to do a similar thing for the y components, right? Our first y component is from this northward portion of his journey. We also have a y component from this last portion of his journey. And so that's 0.35, the hypotenuse, times the sine of our angle, 45 degrees. And so that gives us a y component of 0.6225 miles. So now to find the magnitude of this resultant vector, we just take the components, square them, add them together, and take the square root, Pythagorean theorem. So 1.076 miles is his displacement. And the angle, using the inverse tangent of those components that we found, so the y component over the x component, gives us an angle of negative 35.35 degrees. So this angle, remember, is measured from east. So that's this angle right here. Now, depending on your particular calculator and the tangent function, it may give you this number plus or minus 180 degrees. So just be careful of that when you're dealing with the tangent function. Make sure that you clearly establish where that angle is being measured from, right? Usually we would measure counterclockwise from east, so this whole big angle. So that's why in the diagram here, I showed specifically that we're measuring this little portion of the angle right there. Okay, as long as you are clear about what it is that you're measuring, either answer should be just fine for your professors. Okay, I think that's the end of this example. Yeah, do you guys have any questions about this example? Okay, I gotta know. Cool. Well, if you guys do have questions, of course, feel free to ask. Feel free to run through this on your own with a calculator at the ready for you. I will caution you as well that if you're using a scientific calculator, you're going to want to make sure that it's set in degrees and not radians. That will make a big difference in your answer. And I mean, I cannot tell you how many people forget to change it from radians to degrees on a test, and then they get all the answers wrong. It's a very unfortunate scenario. Professors are usually somewhat sympathetic to that. They might take off a couple of points, but yeah, definitely get used to doing your physics work in degrees rather than radians. Okay, so I want you to take a look at this problem and give it a try yourself. I'll just give you like a minute or two to think about it. Naruto is running at 19 meters per second in a direction 105 degrees counterclockwise from east. How should I set up my equations to find the components of his velocity? So I'm going to pause the recording really quickly, let you think about this for a minute, and then we'll come back and go through the answer. All right, hopefully that was enough time for you to think through this at least a little bit, maybe start sketching out the problem. But our correct answer is A, to find our components. Remember, north would be our y component, east would be our x component. And our angle, if this is our coordinate, our angle, I need more fingers, is measured here, counterclockwise from east. And so that would give us an answer of 19, which is our magnitude, our hypotenuse, 19, times the sine of our angle. And then east would be, again, our magnitude, or hypotenuse, 19 times the cosine of our angle. Okay. All right, here's another example for you to try, just really quickly. Naruto is again running 19 meters per second, 105 degrees counterclockwise from east. So what do we do if we get these component values? X component of negative 4.92 meters per second and a Y component of 18.4 meters per second. Take a second, think about this. We'll come back together for the answer in just a moment. Awesome, I'm seeing some answers in the chat. Great job, guys. Yeah, so in this case, C is our correct answer, right? So let's just talk through these options really quickly. Negative velocities are impossible because they are scalars. That's incorrect. Velocity is a vector because it tells us not only how fast he's moving, but in which direction. The kind of concept related to that is a scalar is speed, because speed just tells us how fast he would be going, but not in which direction he's going. So B, take the absolute value, then you are done. Nope, that would give you a magnitude, but that wouldn't really help us in any way. Okay, C, a negative velocity east means you have a west velocity component. That is true, right? We think about our graphing coordinate axes, right? Up and right are positive, so north and east are positive. And so down and left are negative, west and south are negative. So if we have a negative velocity east, that means we're moving west. So similar to that, D, a positive velocity north means you are heading exactly south. No, because north is positive. So if we have a positive north velocity, that means we're heading north. Yes. Okay. And then I think this is the last question that I have for you to give it a try today. How do we find the magnitude and direction of the following velocity? So here are the same components that we had on the last slide. How do we find the magnitude and direction of the resultant velocity? Take a moment, think through this, and then we'll come back together to talk about it. All right, yeah, it's important in this one to make sure that you read the options very carefully because some of them are very similar, just like your professors will do to you when you take their tests. So let's see our correct answer. It is A. The magnitude is the Pythagorean theorem of the velocity components. So remember, that's the square root of x squared plus y squared. The direction is the inverse tangent of y over x. Now compare that to option B, where it says direction is the tangent of y over x. Compare that to option C, direction is the inverse tangent of x over y. So these are all pretty similar options. You want to make sure that you're reading very carefully and answering correctly with option A. All right. So just really quickly before we go then, here are a couple of just quick review problems for you to think through. We don't have to do this right now because I'll be posting this PowerPoint on Canvas right after class. So you'll have a chance to kind of think through these review questions, but these would be the types of questions that you might see on a quiz or a test that would follow this chapter. And then these are the resources that I'll be posting on Canvas as well. If you want to practice vector addition or drawing vectors or breaking vectors down into their components graphically or with the trig functions, some problems from the book that you might be assigned as homework problems in an actual physics class. These will all be posted there for you. And again, I'll be posting solutions to these in a couple of days once you've had a chance to work through these if you would like to do so. But do you guys have any questions about today's topic? All right. Well, if you do have questions, I'll stick around for a couple of minutes after class to answer whatever questions you might have. But otherwise, we are done for today. Thank you so much for your attention and participation in the chat and verbally. I really appreciate it. So have a great day, and I'll see you guys tomorrow for the start of chapter 2.
Thank you. Have a good day.
Yeah, bye.
Thank you.
You're welcome.